Hello everyone. Um, I hope you're doing well. In the previous class, we studied a couple of things, including we see that we studied about logic gates, and we saw how we can create circuits that are able to do things. We also looked at the electrical component called a transistor, and we saw how it can be used in interesting ways to build these logic gates. We also did a brief history on Boolean algebra and the theory information to get to know how these ideas of using electricity and representing data can be used, or rather is being used currently to build the computers. Other than that, we also did some basic logics, like we did a NOT gate, which was an inverter which we are able to show, and we also did an AND gate and an OR gate, and also we had to mention other kinds of gates. The good thing, we also saw how they are able to be implemented in the electrical form. We saw this using the Circuit.js, and and that is okay. And today in this class today, since we understand the logic gates, we are going to now try to see how the logic gates are combined to do various things, like building calculators, building memories, being able to encode whatever data that we want, basically whatever a computer can do. And in this class for today also, from today's class onwards, it's going to be a bit more engaging in such a way that we're going to play or just follow a guide in form of a game that enables us to guide us to be able to build the computers that we want. And but before that, we need to understand what we're trying to achieve from now till till the end of this course. So as per now, we do understand, we've answered the question of how does a transistor work as an electrical switch. We have also studied about how do transistors form logic gates, which we did in our previous class. We saw how we are able to combine the transistors electrically to build logic from it. And now from today's class, we're going to dig deeper into that and just move a step at a time, but in the direction of how do logic gates perform computation. We're also going to see how do logic gates create memories. We're going to see components like flip-flops, registers. Of course, you've heard of a memory called a RAM. We are also going to see how a CPU is built from these basic components. We are going to build an arithmetic logic unit. We're going to do registers, as we've mentioned, program counters, instruction registers, clocks and buses, and the CPU. We understand the CPU architecture, the fetch, decode, execution cycle, how numbers and characters and instructions are represented in binary. We're also going to see what is machine code, and how does the CPU interpret it. We also see what is an instruction set. We're also going to, we're going to see how instead of writing raw binary, we're able to build simple languages, which are these instruction sets architecture like assembly to enable us to write simple programs. And that's just showing us what we're going to do in the future. But I guess we'll just start small and we see how it goes. Yeah. And in today's class, we are going to introduce to you this guide, or it's going to be our guide. It's called Turing Complete, which is in form of a gate. So I hope you guys follow. So let's get started. It says, congratulations, you have been abducted. So Turing Complete is a game that it's going to help us or teach us step by step how a computer actually works, how we are going to utilize these simple gates that we saw in the previous class to actually build something that is able to do things that a computer is going to do. It's basically a computer. We're going to understand all the principles. So the game is the campaign mode is set up in such a way that the story is that the player, which is us, they are abducted by aliens who are testing our intelligence, and they're instructing us to build components like adders, memories, and all that. And our aim is not to get eaten by aliens. So yeah, hope you do your best and not get eaten by aliens. So we get started. We are testing you. The rules are simple. Build a functional computer and you will be eaten. So good luck. That's the only thing we get. So let's hope we not get eaten. As you can see, we have an input. This is an input and an output. Think of this as a part of that input circuit, a part of that circuit that's going to be able to do stuff. So yeah, and if we turn off the input, we're supposed to see the output as off. So off, the output goes off. Notice that the output component is turned off. This is because the signal stopped flowing from the input component. Next level. Yeah. So we are very impressed with how well you're able to complete the last test. The previous test was not that bad. It's just simple line. Continue. We have decided that you're probably not a plant. So we have a bit of intelligence. So let's see what the next puzzle will be. In this level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level, or you get stuck in the next level. So in the previous level, I don't think we just mentioned about what an AND gate. We just mentioned an AND gate, and a NAND gate is basically, we said that a NAND gate is an AND gate but negated. It's like not we said not AND, right? So we are supposed to do an AND, then negate it in order. And we also, this is the truth table, kind of the truth table. So we are tasked to create this NAND gate. So let's continue. Oh no. The problem with this is that I guess I had, let me see. What does an AND gate do? Okay. As we said, an AND gate takes two inputs and is able to compare them, and if both are true, it outputs a true. But an NAND gate, which is different from an AND gate, does the opposite of what an AND gate by negating the output. So as we can see, the input is off, input 1 is off, input 2 is off, and our output is on, which means that over here we are supposed to expect an off, but then the AND gate kind of just turns it to an on, right? So let's see. Yeah, that's an AND gate. And if we turn both of them on, on an AND gate we're supposed to see the output as on, but then it's inverted, and any of these combinations is going to yield an on or a binary 1. So let's invert, and it's still on, and only when on, both of them are on, then it is off. And I guess we are done. Oh yeah, so we're supposed to find if input 1 and input 2 are both off, the output is off. So, or the output is on. And if one of them is on, that means all of these are going to be off. No. This is off, so it's going to be on. And on, let's just do it on and off, and we can see the output is also on, and this inverted also on, and when both of them are on, then the NAND gate, the output is off, so this becomes off, and check. And correct, you have been unlocked. You have unlocked the NAND gate. With this component you can build everything else in your computer. Believe it or not, using just this NAND gate you can build everything. Yeah, everything, totally everything. So I hope you are excited to get to discover how you're able to do this. So we now have one component, which is a NAND gate, and onwards. Now that you have unlocked the NAND gate, it is time for you to build a circuit. So let's continue. The last level you made, last level you made the table that described the circuit. In this level you build the circuit that describes the table. Last time we had a circuit and we built the table, but now we have our desired output, and now we are going to kind of build a circuit from it. And this should be easy because we have already done NOT gate. So we're supposed to build a NOT gate. And close. A NOT gate, as we studied, was something that takes in an input and inverts it. So if the input is on, this should be off, and if this becomes off, this output should be if this becomes off, it should be on. So let's see how we can do that. And we only have just one component which is an AND gate. Okay, let's see how we do it. Okay. So we want to see that for NOT gate, if input is what do you mean? Oh, we're trying to build a NOT gate, so let's see. I'm not even really sure how to do it, but let's see. We have, if we have an input, but we have to have 2 inputs. Of course, this is not the answer, but we're gonna see if the circuit is able to invert our signals. So if our input is off, we're supposed to get an on, right? And if our input goes or on, supposed to invert it. So let's see. Oh, that was easy. I didn't expect it. And we can see now the signals are kind of interchanging. Yeah. So input on, output off, input off, output on. So I guess we're done. And we can test our output, test it. And now we have unlocked a NOT gate. And remember, this is just from the NAND gate that we created at the start. And let's continue. And you said an AND gate is just an AND gate, but with an inverter, with a NOT gate. Let's continue. Today we are going to do the AND gate as well. We're also going to do NOR gate and OR gate. So right now, the elephant is dominating all the other test subjects from Earth. Adjusting from for brain size, you're also doing well. Thanks. Create the circuit that matches the table. The tip is double click a component to move it together with the connected wires. Okay, so today we are going to build an NAND gate. Or an AND gate. An AND gate, usually its truth table, as we can see, it's going to accept 2 inputs, input 1 and input 2, and only if both inputs are true, then the output is true. If either of them is false, then either or all of them are false, then it's going to output a false. So I'm assuming that since we have a NAND gate and we also have a NOT gate, probably we're gonna have to use them. So we have a NAND and a NAND and the output. So if both outputs are off for an AND gate, we expect the output to be false. So we can place this negation over here to get our desired output. And if either of the outputs is on but not both, we are supposed to get also a false. And only if both of them are true, then we get the true. So let's see. We turn just one input on, and it's still off. And if we turn also just one, the output is still off, and only if we turn both as on, then the output becomes on. That's an AND gate. In this case built from an AND gate and a NOT gate. And I am sure we are okay. Let's test our input. 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 And we are okay. And let's move on. And our next class is on, let's start with OR gate before we get to NOR gate. So you should be happy you get to participate in our glorious test. Okay, you get a chance to communicate with the very advanced people from the galactic civilization. Okay, create the circuit that matches the table. Double click on the component. Okay. So for now we are trying to create an OR gate. As we saw in the previous class, an OR gate is basically looking at two inputs, and if one of them is correct, then the whole statement is correct. That's an OR gate. Different from an AND gate. If both of them in an AND gate are not correct, or either is not correct, then the whole statement is nullified. But in this case, if just one of them is true, then the whole statement is true, and only if both of them are false, then the statement becomes false. So let's see how it goes. And I guess this is just going to be different from the ordering. The previous one we had for an AND gate, we had this structure. And this was an AND gate. And if we test, it's going to be false. It's not going to be true. It's going to fail. And the funny thing is that by just changing the order of the circuit, we're able to change how it works. Like in this case, let's see, our first test case, we're given output as off and off. If both of the outputs are off, we're supposed to get an off, and we do get an on, so there must be a problem. Okay, let's try probably adding this. Okay, and it becomes off. And if one, the first output is green, on, and the second one is off, and we get an on, and which is the exact result we get over here. And also, if we interchange them, this becomes off, this becomes on, still the output is green, which is on. And even if we allow them both, and so now both inputs are on, and the output is on. So this is an OR gate. And we notice that by just changing the order of these gates and probably chaining them in very interesting ways, they're able to do, I'd say, really interesting things. But let's not go beyond where we are. And yeah, let's see. Test. And now we have unlocked the OR gate. And I guess in our final class we're going to do the NOR gate. As you said, the NOR gate is essentially just an OR gate that we've created but negated, right? By negation I mean it's inverted. The bit has been inverted. So, no. Most creatures on Earth are aggressive and cannot focus. To succeed, you must learn to think logically while not destroying things. Okay? Create the circuit that matches the table. And we know what we're trying to match this table is an OR gate, which is, okay, they haven't given us an OR gate, but we already know how to build an OR gate, which in this case it's two of these NOT gates. Okay, need to delete one. Two of these. And our output. So this is an OR gate, but remember it's an NOR gate, which is or not. It's OR but not. It's weird, but yeah, it's the opposite of what our OR gate gives us. So if we test this, it's going to fail, as we can see. But if we negate this output, we already now have an OR gate, which is doing the opposite of what an OR gate would do. Remember, this is just one signal, part of a circuit that we are constructing that is able to do things that we're gonna see. So in our first test case, we are given both off, and we are told that if both of them are off, we are expected our desired output supposed to be on, which is what we get over here. And if input 1 is green, which is on, and input 2 is off, we're supposed to get an off, right? And that's what we get. And if we invert it, still the same, we're supposed to get off, on, becomes off, and only when both of them are true is when we get a false. Okay, I thought that was like an AND gate, but I can see it's different since the output is different. And for an AND gate, if both of them are true, is only when it is true. But in this case, it's kind of just doing whatever opposite thing that an OR gate is supposed to do. So by having both of them true, since this is true, it's turned to false. And if we test, we can see that our first test is able to pass, our second test is able to pass, our next test is able to pass, and our final test is able to pass. And now we have an OR gate component. And I guess we are going good. We're just moving well across this guide. So I guess that's enough for today. And yeah, there's really too much to cover over here, but we're gonna cover them in our next lessons. So yeah, I hope you have a good day, and bye.